Hi, everyone, and welcome to episode 2 of the Uncast podcast. As usual, I am your host, John Panazzo, Chief Strategy Officer for Unraid. And for today's show, I thought we'd do a bit of a deep dive on one of our most popular features of Unraid 6, virtualization and specifically GPU Passthrough. Now, what I want to start with is really the history of this feature, and then I want to go through some best practices for using it and some recent updates. So, for starters, let's go through the history lesson. So for those that don't remember or weren't around at the time, Unraid 5 was a 32-bit based operating system that had no support for virtual machines nor containers. It was truly designed as a pure NAS platform, not an application server or a virtualization host. And if you wanted to run applications on version 5, you'd have to find plugins for them. And the plugins would then need to download and extract the various components needed for whatever application you were loading, and it would install them directly onto Unraid itself. This also meant the plugin authors would have to compile the applications and any dependencies on their own to ensure that they would work on Slackware, which is our base distro for Unraid OS. So this was kind of a struggle for plugin authors because it's not, in the Windows world, we're all familiar. You go to a website, you download a program, you double-click the MSI or EXE file, and it installs, and you're off to the races, right? And the people who make the software, they're the ones that provide that executable or that MSI file that does the installation for you. In the world of Linux, it's not the same. Basically, software developers build their software for Linux, but then it has to be compiled for specific distributions because every distribution can kind of put things in different places. So you have to know what's unique to that distribution when you're compiling an application. And so while there are plenty of applications that are pre-compiled for Slackware, there's even a website called Slack Builds that you can use to find pre-compiled apps. But not every app that's made for Linux, or every package, I should say, made for Linux, is pre-built for Slackware. So for some of these applications that plugin authors would want to build, they'd have to go and find the source code for the applications and then run a build on that code to then make it work for Slackware, and then it could work on Linux or work on Unraid. So it was not as simple and straightforward as things are today. So that was Unraid 5. So for version 6, we knew we wanted to provide a better way to add applications to Unraid, and that's where virtualization came into play, and ultimately was what got me to join the company. So for me specifically, I didn't just want to use VMs for things like Plex or BT Sync or whatever server applications you're looking for. I was specifically interested in GPU Passthrough. And this would be a key feature for us, which is what I was focused on at the time. And it would provide a solution for users to consolidate their desktop and server into a single physical machine. So instead of having to budget for your server's needs separate from your desktop, you could combine the budgets into one machine, get a better processor, more memory, better graphics card, and thereby get a better overall system that can perform better for both your server and desktop needs. But it was quite a journey to get there. So initially, when we started working on this, we tried using Zen. And one of the main reasons for that was that I had previous experience working with Zen Server from Citrix, and Zen was simply the open source version of that hypervisor. So there was some familiarity there. You start with what you know, right? Now, Zen differs from KVM a little bit, which is our current hypervisor, in one key way. So while Zen is its own independent project based on Linux, it in and of itself is not a part of the Linux kernel. So for those that are interested in the technical, basically what happens is you boot Zen, and then Zen chain boots whatever OS you want to run as what we'll call DOM-U. So there's DOM-0, which is Zen, and then there's DOM-U, which is the first OS that you're loading under Zen, but it's not a virtual machine. That is the distribution that's running directly. And then you'd have additional DOMs, which DOM means domain, for any additional VMs that you're going to run. So it's a slightly different method to loading the hypervisor separate from loading the host OS. Now, one big advantage, however, that Zen did provide over KVM was the ability to run Linux-based guest VMs without needing hardware support on the CPU or motherboard for virtualization. This feature was known as para-virtualization. So there were lots of CPUs out there at the time that did not have Intel VTX or AMD V on the chipset, which meant that you couldn't create hardware-assisted virtual machines. HVMs is the short name for it. And so for those users, if they were to have upgraded to Unraid 6 and all we had was KVM and that was it, they wouldn't have a solution for application support. They would still have to use either plugins or just not use applications on Unraid because they wouldn't be able to spin up virtual machines. But Zen, because of this para-virtualization feature, Linux-based VMs could run on processors that did not have any type of hardware-based virtualization support. So this was a huge feature. This was honestly one of the main draws to Zen because it provided an application hosting platform that wasn't hardware dependent. But as we were going down the route of working with Zen, we found out about Docker. And Docker containers kind of stole the show by providing the same benefits of Zen as far as para-virtualization goes. Like you didn't have to have hardware support to run Linux-based guests, and they actually made it leaner and easier to use. So in addition, Zen had a number of problems with GPU passthrough, and the developers of Zen didn't really seem focused on making that a priority to resolve. The reality was that the majority of people using Zen were people doing it in data centers or cloud environments or business enterprise environments where they're running lots of traditional server-based workloads, not home users that were tinkering with GPU passthrough because they were technology enthusiasts. That was not the main use case for Zen. And so we did a lot of research trying to figure out what other things could we do to make Zen work better for GPU passthrough. And there was just so many dead ends. There were no threads to go on that really would improve the experience, and we had a lot of problems with different hardware. So it just became this thing that didn't make a lot of sense for us to pour more time into because, well, once we had Docker, we were like, well, wait a minute. With a VM, even a para-virtualized VM, the user is still responsible for installing an OS, right, a full operating system, adding whatever software dependencies are required for the application they want to run, installing that application, patching and managing that application, and then if you wanted, from a network standpoint, to have even more control, there are all these different things that you would have to do to then optimize that. And so it put a lot of work on the user's plate, which would have been better. It still would have been better than what we had in Unraid 5. But when Docker became a thing and we started looking at it, we started realizing, wait a minute, this thing, even though it still doesn't require any kind of hardware support, it's still leaner than Zen. You don't need as much storage for each VM because of the fact that it can deduplicate the different layers of the containers that you're running. So there was just so many like Docker just literally took the best feature of Zen and did it better. And so once we had that, we started questioning, well, wait a minute, who's running a para-virtualized VM if you have Docker? What could you do in a para-virtualized VM that you couldn't do in a Docker container? And what we found was not much. There might be some very specific, nuanced use cases that I can't even give you off the top of my head that a more savvy user than me would tell you about. But let's put it this way. Ever since we ditched Zen, no one has even broached the idea to us that there was something that they could have done with Zen that they couldn't do with Docker or KVM. So that was the impetus for us to switch. One of the main impetus for us to switch from Zen to KVM. So being, another thing worth mentioning here with KVM was that, again, Zen was not directly a part of the Linux kernel. There were drivers for Zen that were in Linux, but Zen itself was a fork of Linux. And so it was kind of in its own world being developed by its own team that had nothing to do with Linux itself, right? Whereas KVM, instead of this whole DOM0, DOM-U, weird chain booting thing, Instead of that, KVM is just a native feature of the Linux kernel itself. So what does that mean to a developer? Well, it means better support and faster updates with new features. That's what it means. Because otherwise, you have the Zen team building the hypervisor product, right? They're building that. And then you've got Linux building a operating system for running, whatever else you want to run, either VMs, Docker containers, software packages, whatever. And so then these two things have to kind of work in concert with one another to deliver powerful features. So if Zen did something that wasn't then enabled inside of the Linux kernel, you'd have to wait. There'd be a delay between the Zen project making a feature and the Linux kernel getting the drivers or whatever is necessary to adopt that feature, the software to adopt that feature. There was a lag time there. But with KVM, because it's built into the kernel itself, the whole project is inherently more supported, right? Everybody in Linux is working on that. And so Kimu, for example, is another project, but it's instead of being in the kernel space, it runs in user space. But Kimu and KVM, they work very much hand in hand. So as KVM enables new features at the kernel level, the Kimu project seems to move pretty quick at adopting those features and getting out release candidates that then have those features and then pushing those to stable. So we just see a lot better support from Linux by using KVM as opposed to Zen. So, and then, as I mentioned before, Zen also had a lot of problems with GPU pass-through, and that ultimately pushed us to checking KVM out. The other big thing that KVM had was a killer feature that most of us should know about by now, known as VFIO. Now, VFIO is a component of the kernel that allows you to bind PCI devices to a specialized driver designed to delegate device management and interaction to VMs running on the system. And this is ultimately the feature that enabled us to do GPU pass-through. Now, VFIO is a project that's led by Red Hat developer Alex Williamson, who I've had the fortunate opportunity to speak with on more than one occasion. Alex is the godfather of VFIO, as well as one of the key advocates for GPU pass-through. So for as much as we might receive credit for making GPU pass-through easy to do on Unraid, without Alex, it wouldn't be possible at all. So hats off to that man. If you see him on the street, pat him on the back, tell him he's a rock star, because he is. And GPUs are only one kind of device that VFIO can handle. Technically, any PCI device has potential to be assigned to a VM, with a few caveats that we'll cover another time. So off we went to perfect our KVM implementation and achieve easy-to-use GPU pass-through for consumer-based cards. And through our R&D, we learned quite a bit about exactly how difficult, quote-unquote, making this easy was really going to be. So first and foremost, you would have to have virtualization and pass-through capable hardware, specifically the CPU motherboard. So for Intel, that meant Intel VTX, and if you want to do pass-through, VTD. For AMD, it's called AMD V, and for pass-through, AMD VI. In addition, your hardware would also have to be able to put whatever PCI device you want to assign into what's called an IOMMU group by itself. And server-grade Intel CPUs shipped with a feature called ACS. And what this would do is it would isolate each PCI device into its own group automatically. Unfortunately, ACS has really only been available as a feature on the highest-end CPUs, the ones that cost a lot of money, either server-grade CPUs that maybe they don't cost a fortune, but they don't have the best performance, or the Extreme Edition CPUs for the desktop side that cost a fortune, right? But they have that feature. So, and it's important to note that ACS is designed as a security feature to prevent I/O from accidentally being delivered to devices that shouldn't receive it. So, unfortunately, this would outright prevent some devices from being passed through because they weren't properly isolated. So then on top of that, you'd also need a GPU that wouldn't freak out when assigned to a VM. We'll explain that a little bit more in a minute here. And even if all of that worked right, some GPUs would cause host-level crashes if the VM was rebooted. So there were a lot of caveats here, a lot of challenges to overcome. But thankfully, we did figure out the right formula to make all of this work for the vast majority of users. And the trick was having really good default values for everything with a few toggleable switches for solving advanced problems with IOMMU groups or hardware-specific difficulties. Now, one of these toggleable things was the PCIe ACS override, which would split devices into their own IOMMU groups, even without ACS being present on the CPU. The other feature was VFIO allow unsafe interrupts, and this would enable pass-through for devices on host BIOSes that allowed interrupt remapping but didn't yet have support for IOMMU groups to constrain interrupt mapping to designated VMs. Now, I know that there have been a couple sentences like that in this podcast so far that might make your head explode. Just know that if you were having an issue with GPU pass-through, you might see an event in the log that says something about allowing unsafe interrupts. And if you turn it on, then your issue would potentially go away. So you might be wondering, what security implications exist with these two workarounds? So let me address that. So first and foremost, if you're the master of the host and the guests on your unraid box, these two workarounds really don't pose any security risk to you. The risk is only when you can't implicitly trust the guests that are running on the system. For example, if you had two VMs running, it would be technically possible with some really advanced know-how to compromise one VM from another or from one VM to the host. But if you are the admin of all the workloads running on the host, it's kind of a moot point. You're not going to hack yourself. And that's why these workarounds exist in Unraid OS by default. But there was one other challenge that we came across pretty much right in the middle of building in support for all this, and it was specific to NVIDIA devices. And in short, at the time, NVIDIA hadn't made any statements about support for using their GeForce GPUs in virtual machines. But we noticed that after a particular driver update, these GPUs that were passed through to VMs would receive a code 43 error, which essentially disabled the GPU from performing as it should. And eventually we discovered that by simply hiding the KVM flag from the virtual machine, the error would go away. So we made that the default whenever an NVIDIA GPU was selected for pass-through. This was definitely a workaround. But again, it wasn't like NVIDIA was coming out and saying, this is a violation of our EULA or anything like that, right? This had nothing to do with licensing terms or anything like that. We simply put in something that made something work, and NVIDIA never said anything to the otherwise. So, good for us. We managed to get something working for the vast majority of people out there that wanted to use this kind of a device. So, that was quite a history lesson to go through, but hopefully it sheds some light on our thought processes and a little bit gives you some little bit of behind the scenes knowledge on how we've optimized Unraid for virtual machines and pass-through. So that being said, let's jump into some of the common struggles, because even with all of that work being done, there are still today constant struggles with VMs and GPU pass-through. And the first thing we got to talk about is AMD hardware. So this is definitely one of the most common struggles we see is when people are using AMD-based CPUs or GPUs for that matter. Now, before I go any further, I want to start by saying I am not an Intel fanboy, period. I'm all about sheer functionality and performance. If another platform can offer better price for performance than Intel, I'm definitely game to try it. But with AMD, the issue is a lack of consistent and reliable results. So before I highlight all the struggles, let me note that standard VMs running on Unraid without any type of PCI devices being assigned to them seem to work just fine. So if your use case doesn't involve passing through a PCI device, AMD is perfectly fine for that. But if GPU pass-through is your goal, you should be aware that this can be a struggle. First, we should mention that by default, the host OS needs a GPU to function, which means that a secondary GPU is needed if you want to pass through to a VM. Intel CPUs have a built-in graphics capability on their chip, not on all chips, but on many chips. So no discrete GPU is required for the host. You already have one, it's through the CPU. And while some AMD motherboards feature a Radeon embedded device, it's far less common, and that is especially true on Threadripper. The second thing we should mention is that AMD GPUs have not had the greatest history of support for function level resets, which is a key component to making GPUs work properly when a VM is restarted. We've seen entire host level lockups and other critical issues due to this. And while some folks have been hard at work to develop quirks for the Linux kernel to try and solve this from the software side of things, NVIDIA devices just tend to work without ever having to think about this because they've had function level reset for a very long time. Another thing we should mention is that we've tested this feature on both Ryzen and Threadripper. Now, Ryzen does tend to work fine, but we did struggle with issues related to power and C states that new users will still sometimes run into today. And with Threadripper, we experience lots of hitching and stuttering issues that we still haven't been able to resolve. We believe it's due to how CCX works on the Threadripper platform and the NUMA nodes that are on those systems. And there just might not be the ideal path to minimize latency, and it just causes weird hitching and other issues that happen on those platforms. And let's not forget about the fact that some users just can't get their monitor to light up no matter what GPU they use on an AMD-based CPU. So that's why whenever anybody posts in the community about a problem with GPU pass-through, the first thing that I look at is the underlying hardware. If it's not Intel and NVIDIA, the first thing that we're going to recommend is switching to an NVIDIA GPU. And if that doesn't work, we would then suggest switching to an Intel CPU. It's not to say that you can't get things to work on AMD. It's just there's a lot more legwork to go through, and it's a lot more hardware specific, like what exact CPU, what exact GPU, what exact BIOS revision, all of those things can play into things. Another thing that I want to mention, switching from AMD for a minute, is when you're buying an NVIDIA GPU, what brand should you go with? And specifically, I want to highlight EVGA. Because sometimes, even with NVIDIA, and even when on an Intel CPU platform, you'll go to pass through the GPU, you'll start up the VM, monitor stays black. What happened? It's just not working right. So sometimes it can be as simple as turning on the allow unsafe interrupt setting, or just switching what PCI slot you're using for the GPU. But other times, those things don't make a difference. So a while back, I had both an Asus and EVGA branded GPU that I was testing with, and both failed to light up the monitor like they should. Now at the time, this was before we started experimenting with OVMF, so we were using CBIOS for everything. And we were just beginning to experiment with OVMF, which is a UEFI BIOS for virtual machines. Both the cards didn't work with the UEFI option either, and it was then that I found out that older cards might not have even had UEFI support on them. So the cards themselves had to have firmware that was capable of interacting with UEFI. So I contacted Asus, and I waited, and eventually was just told that if I needed that feature, I would need to go buy a card that had it, even though they don't advertise that feature on the box. And keep in mind, I had bought this card a year before I was asking for this support. So it wasn't like we're talking about a card from super long ago at the time. They had no interest in worrying about my use case and adding that feature. But with EVGA, I was emailed back in less than an hour, and they provided me with an updated VBIOS for my GTX 650 at the time that immediately resolved the issue. And it's for this reason that I cannot recommend any other branded GPU than EVGA at this time. Their commitment to fantastic customer support is the main reason. So if you're planning a build, go with an EVGA NVIDIA card. Doesn't mean that other brand cards won't work, but I'm just going off of my personal experience that I had, and every GPU that I've bought since then for testing has been EVGA, and I've yet to run into one that doesn't work. So they're not paying me to say this, by the way, either. I'm just telling you this was my experience. This is why I make the recommendation. Okay, so the next thing I want to jump into is performance tuning, because let's say you get this far. You get your monitor to light up, you get Windows to install, and you're like, wow, I'm gaming in a VM soon. Wait, why is it hitching? Wait, why is it lagging? Uh-oh, this isn't bare metal. John lied to me like that. So let's talk about how to make that performance as close to bare metal as humanly possible. So there's really two things that you can do to make that performance as solid as possible. The first is CPU pinning. So almost every CPU nowadays has multiple cores, and in addition to that, CPUs have a feature known as SMT, symmetric multithreading, and more popularly known on Intel as hyperthreading. But just to be clear, hyperthreading is just the marketing term that Intel uses. The more generic way to explain this is just SMT, symmetric multithreading. And what SMT allows is a single physical CPU core to present itself as logical CPUs known as threads, and the ratio is 2-to-1, logical to physical. So on an 8-core processor with SMT, you would have 16 logical CPUs present. Now, when you create a VM, you can designate how many virtual CPUs that you want that VM to have, and it's not limited by the number of logical CPUs on the host either. So by default, KVM will automatically delegate jobs running on those virtual CPUs to the logical CPUs on the host based on which of those logical CPUs is best suited for the task at the time. This way, if there are lots of different processes running, KVM can determine which should run and where. Now, while this is perfectly acceptable and suitable for most server applications, this method of CPU scheduling can lead to abysmal performance for VMs with GPU pass-through, and specifically gaming. And every time KVM switches which logical CPU is handling the functions for the VM, it causes context switching on the CPU, which means that the previous logical CPU that was handling the job has to dump everything to a temporary location, then move the job to a new logical CPU, and then start up again. And what this feels like in a game is hitching, where the video frames stop momentarily like someone hit the pause button twice really fast. This is obviously unacceptable for gaming and other real-time performance tasks, so to get around it, we need to pin the virtual CPUs assigned to a VM to specific logical CPUs on the host. And more specifically, we need to ensure that for each virtual CPU assigned, each CPU core on the host and its SMT pair is pinned to only run on those threads. So if you were ever curious which logical CPU is paired to which hyperthread, you can actually check this out on the CPU pinning page under settings in Unraid, and you'll see all the logical CPUs and their hyperthreaded pairs listed there. So just to give you an example, on one of my systems at home here, I've got an i7 8700K CPU. It's a 6-core processor that supports hyperthreading, which means I have 12 logical CPUs in Unraid to work with. So to maximize my VM's performance, I've pinned 10 logical CPUs to my guest, specifically CPUs 1 and 7, 2 and 8, 3 and 9, and so on. This ensures that QEMU keeps the virtual CPUs and the logical CPUs aligned so that the hypervisor itself doesn't try to reschedule those virtual CPUs to other logical CPUs. I know this is a lot to follow, but hopefully this is all making sense for you guys. Now, pinning is great, but the second concept we have to discuss is CPU isolation. Now, by default, Linux will automatically make use of any and all available logical CPUs that are running on the host, regardless of what CPU pinning you've done. Pinning only prevents the virtual CPUs from jumping into other logical CPUs. But what stops the host from trying to run processes on those same logical CPUs as my VM? CPU isolation does. So what isolation does is it tells Linux to ignore specific logical CPUs unless explicitly told otherwise. So for my VM, I isolated the same logical CPUs that I pinned. So 1 and 7, 2 and 8, etc. If I didn't do this, and someone started watching a movie on Plex while I was gaming, it's possible that Linux would try to perform some of the transcoding work using the same logical CPUs as my gaming VM, causing massive hitching and stuttering during my game, causing me to then rage and break a monitor, a keyboard, or any other peripheral within striking distance. So by isolating, that doesn't happen, and I don't have to spend lots of money replacing my monitor, right? And we get good performance, we get good stability, and we get good consistency. So again, let's summarize the best practices for GPU pass-through. So first, stick with Intel and nvidia if you want guaranteed results. You can opt for AMD, but just know that there are more struggles there, generally speaking. Make sure that you have one GPU for the host and one for each VM that you want to use with this feature. And then make sure you pin and isolate the CPUs that you intend to use for your VM. And lastly, if you run into problems with black screens or other assignment issues, you can try turning on the VFIO allow unsafe interrupts toggle or the ACS override. And for those that want to stray away from that advice and walk the more difficult path, I highly encourage you to watch Space Invader 1's Advanced Pass-Through Techniques video on YouTube. I cannot say enough about Space Invader 1. Ed is an amazing individual who has really done quite a job in providing people with all of this advanced knowledge that we wouldn't feel comfortable putting out there ourselves because it's a little complicated to do some of these things. But if you're in that situation where you're like, hey, I have this specific hardware, I don't want to go spend more money on different hardware, how do I make what I have work? Following Ed's guides, you have a higher chance of achieving success. So check him out for sure. And then the last thing that I do want to mention, I mentioned this on the last podcast episode, and I'll just bring it up here again. So earlier in this episode, I mentioned that with NVIDIA that they had at one point kind of stopped allowing the drivers to work inside of a VM, and then we had to build in some circumvention to get around that. But back in March, NVIDIA added support on their knowledge base for this use case, specifically with GeForce class graphics cards. So that's a huge deal that they did that, and we still have to go through testing to see if it has any impact to actual performance, or if we can do NVLink now that that's the case. But this is huge because this means that we don't have to worry about them kicking rocks on us in the future. So a huge shout out to NVIDIA for doing that. I'm glad that they're officially supporting it, and I'd love to see something similar from AMD. I'd love to see a bigger commitment from AMD to making things like function level reset work ubiquitously. I'd love to see if there was a way for them to push out either a vBIOS or driver update or something that would take care of this. But yeah, I'd love there to be more competition in the GPU pass-through space. I'd love to stop having to recommend NVIDIA all the time, because as much as I think they make good products, competition breeds innovation, and it'll drive prices down for everyone's. So if you know anybody at AMD and you can kind of beat on them about it, please do. We've tried in the past, and I mean we've gotten a hold of people at AMD. We've had conversations, but it didn't go anywhere. So all we can do is keep tooting our horn, and hopefully they'll hear it. So all right, well, that's going to cover it for today's episode. I know this was a very specific one, focused on a very specific feature, but this topic comes up a lot. We get a lot of questions about it, and there are still people today that struggle to get good performance. And so hopefully the advice given here and the history lesson kind of explains the background of why we did this, how it works, and what you can do to get the best performance out of your system. So stay tuned for our next episode. Follow us on Twitter if you're not already, and we'll catch you guys again soon.